All right. Hello, everyone. Welcome to the MIT Mobility Forum, designed by the MIT Mobility Initiative. I'm Jinhua Zhao, Professor of Cities and Transportation at MIT. I'm so glad that we have two extraordinary innovators joining us today, Professor Daniela Roos, the Director of CSAIL at MIT, and Dr. Heidi Wyle, the founder and CEO of Venti Technologies. Today, we'll really explore the cutting edge of self-driving trucks, focusing Venti's work automating container transport at Singapore port, the PSA, which is one of the biggest the port, where their autonomous fleet is already operating in the real world conditions. We'll also dive into the power of combining language and video to enhance the art of distribution generalization in AI mobility models, where Professor Roos will give the latest on the VIM. Also, as mentioned, we'll have hopefully 5 minutes to talk about the DeepSeek. Many people will be interested in that topic as well, right? So before I give the forum to Heidi and Daniela, I do want to motivate the audience a little bit. In the chat, please type in your organization, city, and the local time, so we know a little bit about the background of the audience here today. So I would say MIT, Cambridge, local time, 12 now. Right. Also, if you can add the large port that's closest to your city, so we know where you distribute in the world there. Let me also emphasize the norm of this forum, which is for all the audience to contribute one idea, either as a form of a question to Heidi or Daniela, or comments. You can type it directly into the chat. Right. Let me introduce Professor Daniela Roos is Andrew and Erna Viterbi, Professor of Electrical Engineering and Computer Science, the director of CSAIL, which is the largest lab at MIT. Daniela Roos studies robotics and artificial intelligence with a specific focus of developing the science and engineering of autonomy. Professor Roos served as the member of the President Council of Advisors on Science and Technology, the PCAST, and on the Defense Innovation Board. He now serves as the US expert for the Global Partnership in AI. Professor Roos is a MacArthur Fellow, a Fellow of ACM, IEEE, AAI, and AAAS. He's a member of the National Academy of Engineering, National Academy of Science, and also of the American Academy of Arts and Science. He's a recipient of numerous awards. I should mention a few: Engelberg Award for Robotics, IEEE Edison Medal, the John Scott Medal, the John McCarthy Award. And Dr. Heidi Wyle is the founder and CEO of Venti Technologies, a global leader in self-driving vehicle system for logistics, including ports, intermodal rail, airport, warehouse, and factories. Venti is a partner with the leading port operator at developing the driverless fleet, shipping container moving trucks in the 24/7 real-world operation. Dr. Wyle founded two previous companies, including Computational Biology Corporation, which is acquired by Agilent Technology. Dr. Wyle won many awards, including the 2024 Forbes 50 over 50, Women in Supply Chain Award, Women in Tech Global Startup Award, Top Tech Startup, and also is the Shark Tank winner, and also named one of the Forbes Top 50 US Women Tech CEOs. In addition, he participates in many of the board volunteering, including the board of MIT, Harvard Medical School, Brown Medical School, and was also the chairman of the board and president of Massachusetts Women's Forum. Without further ado, let me pass the forum to Dr. Heidi Wyle. Heidi, please.
Well, thank you. So it's really wonderful to be with all of you today. Daniela is really, as I said, a legend in her own time. You heard all about her, but it will be fascinating to understand how her science and technology got translated into this company that I'm running, and how we have actually operationalized autonomy. Jinhua, thank you so much for the invitation to be here. I love the picture of MIT behind you, and we will work really hard to stand to the hurdle that MIT holds us to. So let me share, and let me go quickly through my slides. Making sure that I keep to time.
Yes, looks great.
So Venti is a global leader in AI-powered autonomous vehicle logistics solutions. we focus on moving goods. So basically, we think of our market as ports, airports, factories, warehouses, and intermodal rail, as Jinhua said earlier. It really is the supply chain, the global supply chain, the US supply chain. That's what we're targeting. Very importantly, we are the only company in the West that has fully operationalized an autonomous fleet at moderate scale. We are not doing 1 or 2 or 3 vehicles. We are doing tens of vehicles. We're the only one. The reason is autonomy is excruciatingly difficult in that you have to live as a vehicle in the real world with all the strange things that happen. And that's why we started, and this is under Daniela's guidance, in the area of enclosed environments. Now, I'll claim, Jinhua, my closest port is Singapore, despite the fact that I live in the Boston area. So our trucks now, each of them move around 250 of those shipping containers per week. And we also have what I can call tertiary level within our software, where we handle things like the reflection and refraction from puddles or from super heavy rain. So the level of nuance and rigor of the system that we have is very strong. We right now have a fleet of tens of vehicles that is looking to double quite soon. And we have moved over 160,000 containers and have run over 400,000 kilometers. Autonomy holds the promise of an enormous value proposition. Basically, we save costs, we increase efficiency, and we increase safety. What you have to realize is that the minute we end up with an all-robot fleet, which is not where anybody is today, the process will be like a second industrial revolution. Right now, as I said earlier to some of you, we now have exceeded human productivity, and we operate with 25% greater productivity than human drivers. We save 70% of labor costs. Obviously, robots operate just about 24/7. And our data shows that we operate 3 to 6 more hours a day. So this is the value proposition. But what I want to tell you, which I hope you understand the implications of, is these huge trucks here, they have a 40-foot long trailer attached to a roughly 15-foot long cab. We operate those babies with a 2-centimeter positional accuracy. Who on this call can drive their car to a 5-centimeter positional accuracy? We are building the future of moving goods because, again, as Daniela steered us 2 years ago, moving goods in yards is much simpler than moving people in cities. And here are some of the supply chain elements that we operate in. Now, Venti's AV system can be thought of as a horizontal technology platform for moving goods, period. So we can span all these different sectors because the core autonomy is just that, a core. And so we build the system with the autonomy that took us a number of years, even after coming out from Daniela's lab. And then we do it by application to a second layer, and at the top is an individual site. So here's the first of the videos I want to show you. What we are doing is we are sitting, we have a camera view in the cab of this truck. It's a fully autonomous truck. This was how we got our big partnership. Here's the computer that's running the system, and I'm going to walk you through this. So we are in a port now. So this is fully autonomous. The vehicle starts off, it saw the stop line and it stops. It takes that left turn, which was protected, just as you or I would do. It waits at the stop line, which, by the way, it sees. It's looking for a hole in the traffic. You can see this is a busy place with all of those trucks running by. Again, it took a right-hand turn. Now it takes a protected left-hand turn. Those lanes that are in gray are the working lanes. The vehicle has to go into that lane. Now watch this. Wait a sec. Boom. That little thing was the 2 centimeter accuracy piece of work that we did. Here, the crane comes up here on the left-hand side. Now watch here in the rear view mirror on the left-hand side, and you'll see the container comes down. You saw maybe a slight shudder on the truck when the container was loaded. It's checking to make sure the container is seated properly. Everything's fine. And now it's going to go. It went to the stop line, and now it's going to continue to drive by itself. It's going to get unloaded. So it stops because it sees this suspended load, which is extremely dangerous. Every now and then these containers fall off. They weigh 8,000 pounds. So the robot knows it needs to wait until the spreader is gone and it's completely safe, which it did. Again, we are going into this working lane. Again, wait here, watch. Boom. That's the 2 centimeter accuracy correction. Now we're doing the inverse. We're waiting for the crane to arrive. Here it is. Again, look at the rear view mirror, and you'll see that the container is getting unloaded from the robot vehicle. Watch the red, there it goes, the red container comes off. And so now the robot wants to go back to where it belongs. And again, it's navigating through its own feature space map throughout completely by itself. These are the big wharf cranes, the ship-to-shore cranes. Here is a ship getting unloaded. You can see the trucks coming to get unload. And again, our robot stops, waits for traffic, gets its break. This is the busiest road in this very busy port. We are running along with a wharf on one side and the storage area, the yard, on the other. And you can see that the robot can change lanes seamlessly. We can also pass objects that are that have stopped. Again, we're waiting for traffic at this heavy port. And this you can see is an area where there are basically only big trucks. So we continue to go, but we stop because we see this truck. The robot realizes it's a threat. Indeed, it is. That truck was backing up right towards us, but the robot, of course, can handle it and stopped. So here we go. You can see that it sees the lines on the ground, and now it's put itself to bed. That we use these road markings as a second orthogonal help for us in addition to the other vertical feature space, so it brings us more reliability. I thought you would be interested to see this from the robot's point of view. This is the truck. Actually, the truck's moving, but it looks to us like all the other ones are moving. But look at the complexity of this environment. The robot truck is navigating its travel through all of these other human-driven trucks. So at this time, we have about 30 trucks that are robots, and they're running around with 900 additional human drivers all around them. So just to give you a quick summary, this is a little bit of a proud person, me, because our team within 2024 clocked this mileage. And what you can see is we started out with a smaller fleet, we built up the fleet, and we build up the mileage. So we're very proud. We actually last week hit our highest level of weekly mileage possible. As I said, again, we now have with these robot trucks surpassed human productivity in terms of containers moved per hour. And you can see that data here. I'll also show you very quickly, this is an airport baggage truck. Watch how close we get to the curb. This is again a 2 centimeter accuracy demonstration. Look at that. Look how we can align right next to that curb in a completely straight line with all 5 of those vehicles. And here it shows you how close the wheels are. The robot did this. Again, the level of accuracy that the robot can get is demonstrated from that. So I don't want to get into detail. I think I'm really almost running out of time, but we have best in class technology. Not surprisingly, we were found out of MIT, out of Daniela's lab. And basically it's a complete AI driven platform, everything we do. I basically say we were AI before AI was a thing. We do mixed traffic, human robot. Importantly, we save tens of millions of dollars for our big customers because we do not need any new infrastructure. We do it all with the software. We can retrofit just about any vehicle on the planet, and we have done everything from a small wheelchair to these big trucks. Importantly, we've developed software tools that enable us to scale quickly, and it is, as I said earlier, a universal stack. We can run through the heaviest monsoon rain that hits Singapore, which we did about 2 months ago during the monsoon season. Not a single one of our fleets stopped. So this shows you a little bit about what the system looks like. We can do any vehicle. We put on all of the hardware that are required to change it, or we can specify new production grade. The operating system is our 70-some million dollar asset at the moment. And in addition, we have these as well, these components as well. Whoops. And so what we do is when we go to a new site, we map, we use a feature space map, again, technology Daniela developed. We define what we need, we test it incessantly, implement. And importantly, we hand off the ops to the customer. So Venti is actually real. We have fully operationalized autonomy, and that's the takeaway message. And we can, here we can, as I said, now we are, this is a long video, but basically what it shows you is not only can we go forward, but now we can go backward. We go backward again with a 4-centimeter accuracy. And the most interesting thing that happened here is when we were doing that, the robot found a more optimized path to back up and lock in the loading dock than the humans had been using. It was just absolutely fascinating that given the robot's computation, it was able to find a more efficient way to get into a loading dock than the ones that all the people had been using. Lastly, we have a fleet management system. And if you think about it for a minute, a fully autonomous vehicle fleet management system enables you to get the human out of the process. And when we get to a one process situation, we can crank down on the effectiveness, as I said earlier, in a second industrial revolution in terms of effectiveness and productivity. So, last thing I'll say is that in addition to doing all this technology development, we also have developed a training program for remote operators, which we put in, and also for, we use the drivers for that. And so we are actually enabling a new class of job to come about, which is these remote operators who work hand in hand with the robot. So that's kind of a summary of what I wanted to show you. The bottom line here is that Venti has actually truly operationalized a significant size fleet running 24/7 and exceeding human productivity. We have opened the door to the great promise of autonomy.
Wow, this is brilliant. Yeah, thank you, Heidi. Before I invite Daniela, just a quick question on the operation side to see really operation at the real context here, right? Last year, I visited the PSA and your colleague showed me the control room. Your colleague is working hand in hand with the PSA authority people there. This is marvelous to see the collaboration. At that time, I think you guys are successfully operating on the yard side and saying we are experimenting on the wharf side. When do you think we can start operating at the wharf side of the autonomous truck?
Well, we have started, and we expect it to be fully operationalized by certainly the end of 2025 and hopefully earlier in the fourth quarter.
I see. You also mentioned your truck can endure this monsoon rains, etc. Another hazard in Singapore is the lightning, very frequent lightning. Are the trucks okay with that?
We've never had an issue with the lightning, Dingwa. I guess
okay.
we could get fried, but we have not yet.
Okay, yeah. The airport side, they really have to shut down the airside the operation during line. But then last one is when we'll see your trucks in the United States?
Oh, that's a great question. Hopefully by the middle of 2025. So
Wow.
we are signing agreements with US railroads, and we expect to have data coming out and the trucks running by the middle of the year for sure.
Wonderful.
Super
Thank
excited.
you.
Yeah.
Yeah, that's
thank you.
wonderful. Daniela, yes.
I think
Can
you're
you see
muted.
Can you see my
Yes,
screen?
can see it. Yeah.
Yeah. So I would just say that it's really so exciting to think about how you go from state-of-the-art research into impact in the physical world. The project that Heidi described started with the MIT Future of Urban Mobility program in Singapore, and so this goes back to 2010. And for a long time, we thought about the technology, the underlying technology. And then eventually the technology got to the point where it was well developed and robust enough to be deployed. But going from idea, maybe we can have a self-driving car, to a research prototype that drives on, let's say, the streets of Singapore is a huge amount of work. Going from a car that runs on the streets of Singapore to an actual product that does what Heidi showed you is like an order of magnitude more, at least. It's just really a lot of effort to go from a research idea and the research prototype to something that is so robust and so capable of doing real work and bringing real value to people. But it's very rewarding. So it's been so exciting for me to be part of this. Now I want to switch gears a little bit and talk about what is happening in research with respect to mobility, and how might we advance the kind of capabilities we have for our research vehicles, and how might we transfer that into actual prototype. And I want to talk about physical intelligence as it pertains to the control of mobility, of self-driving vehicles. So physical intelligence, or physical AI, is when we use AI's ability to understand text, images, and other online data to make robots, to make real-world machines, robot trucks, more capable. Okay, so I'm sure you have all played with large language models and chatbots, and you have seen text generation, you have even seen image generation. And so the question is, can we somehow combine those extraordinary capabilities with physical action, with perception and control? Because if we could do that, then we could expand or we could move our algorithms that are currently forced to think about pixels and XYZ coordinates into a space that is much more abstract, because we can use language instead of pixels and XYZ coordinates. So let me show you an example so you can understand what I mean by this. So suppose you have an image and some text describing it. Is it possible to, why is this auto advancing? Is it possible to combine the image representation with a text representation in the same foundational model in a way that allows us to go back and forth between the textual description and the visual description of the scene? So if we could do this, then we could train machine learning using images like the one you see here. And so, for instance, we can say, we can show machine learning an image that shows a car avoiding a deer. And we can train with a lot of video data how to avoid the deer. And if we can do that once, then we could expand into out of distribution scenarios, into scenarios that the vehicle hasn't seen yet, to say, okay, you learned how to avoid the deer, now also avoid benches and trees and other animals and people and trucks and vehicles and anything else you want. Here's how this works. So in fact, the answer is yes. And the way it works is by finding a set of textual features that are relevant to driving, and by associating those features with visual features that correspond to the same kind of concept in the image. So we can go from text to curating a set of textual features that can be swapped in as simulation targets into our system. So let me summarize. We have a multimodal representation that has videos, images, and text. This allows us to train on videos, and then we can we can describe those videos in words, and we can see what is the correspondence between things like trees and cars and people. What is the pixel correspondence to the text correspondence? And once we establish these correspondences, then we can use the policy that was learned by looking at videos. We can use that policy and we can extend it to do the same action in many other different scenarios. And so, so in particular, this is a simulation that shows how we can use videos to train a self-driving vehicle to drive in the woods to avoid cars, like one you see here, so to not crash with cars. And then using this idea, using the policy trained to avoid cars, we can also extend the policy to avoid animals. And we can extend the policy to do many different things. We can avoid animals, we can drive in different lighting conditions, in the snow, in the rain, at nighttime, in urban areas, in rural areas. And this is actually very powerful, because if we had to use today's state-of-the-art solutions to train policies that can capture all these different examples, we would have to spend enormous amounts of energy, and we would have to look at enormous amounts of video. So this is really what is called zero-shot out-of-distribution generalization, where the idea is you train in one domain, and then you have some representation that allows you to go back and forth between that domain and many other domains. And so this is a very powerful aspect of physical intelligence and of mobility, because now we can use language and abstract concepts in order to build on a kind of a foundation that was built using pixels and using XYZ coordinates. So this advance, you can imagine how this would be very powerful in the application that Heidi talked about. We have trained our self-driving trucks to deliver containers in a rail yard, which looks quite differently from so we've trained in a port, which looks quite differently from a rail yard. But using language, we will be able to much more quickly extend those solutions into completely new environments. Now, another thing that we have been thinking about is how do we avoid mistakes that AI solutions make? And so the solution, the autonomy stack that Heidi describes does not make mistakes. But there are other AI purely vision-based models that will make mistakes. As you might know, a self-driving vehicle uses both lasers and computer vision as inputs to identify where the obstacles are and where the vehicle is in the world. Your Tesla uses only vision. And so the lack of LiDAR feedback is problematic, because your Tesla sometimes makes mistakes. Your Tesla sometimes cannot use the camera alone to detect an obstacle or a group of obstacles. And so we've been thinking about this this question just as a way of providing more robustness and safety for self-driving vehicles. And so the question is, how can you avoid crashes? How can you avoid crashes at all times? And so here's the solution. It turns out that we can take a machine learning model and we can wrap it with an additional layer, a single layer, which is inspired by the control theoretic community. And that layer we have called barrier net. Now, barrier net implements a mathematically defined set of constraints that forces the output of the machine learning model into a safe region. So you can define constraints that ensure that there is no crash for an autonomous vehicle. You can define a set of constraints that ensures the output of a machine learning model is not toxic. You can express many applications and problems in the physical world in mathematical language that ensures that the output, which may have been faulty, is actually safe. And so if you want to see a little bit of detail, essentially, we can use high order control barrier functions in order to specify barrier net. And then we have a method that maps the high order control barrier functions onto a high order control methodology that essentially translates this mathematics into convex optimizations that can be trained using traditional gradient descent solutions. And so with that, we are now able to ensure that the output of machine learning-based solutions for mobility is safe, even if you only operate on camera. And so here you can see some really challenging cases that are challenging for your Tesla and in general for autonomous driving that uses camera only. You can see applications in the winter. You can see applications when the sun essentially obscures the image, and when you have strong sunlight. So this is very powerful, because now if we can actually specify mathematically what it means for an AI solution to be safe, we can build this barrier net and wrap it around any kind of machine learning model, and we're guaranteed to have a safe solution. The solution is quite generalizable. Here you can see it applied to a situation where a plane has to fly in a stable way. It has to hit these stars, and it has to not crash. And the solution is doing really well. You can even apply the solution to fleets. And so here we have a case of a fleet of about 200 vehicles that are exploring together a complicated environment, and they have to travel together through these holes, but without crashing into each other. And you can see that's a simulation, and you can see now the same solution applied to a group of robots that should not crash into each other and should move a heavy object that a single robot alone cannot move. And so, so my point with these examples is that the latest advances in AI can be adapted and implemented on mobility applications. They can deliver to us higher levels of reasoning, more intuitive human-machine interaction, and safety or safe solutions, safety control, and safety-based AI solutions, which are very important for mobility applications. And with that, let's pause and answer questions.
This is marvelous. Daniela, this is the third time I invite you to speak at the Mobility Forum. Every time you bring such a refreshing, new advanced research here. This is amazing. Thank you so much. Yeah, we don't have too much time now, but Daniela, we talk about, many audience are very kind of intrigued about the DeepSeek. You prepare a little bit on this. Can you share with us that as well?
Sure. So let me see. Hang on just a second. Maybe you can ask, I have to find the slides.
Sure.
Maybe you can ask Heidi a question while I put the other slide deck up.
Yeah, maybe Heidi, talk a little about how you and Daniela restarted the collaboration. Where's the ambition of coming from, moving from a lab innovation to an actual real world business? Tell a little bit about the history.
My dining room table.
Oh,
So that's literally the truth. So we were interested in working with Daniela, myself, and a couple of other MIT related people on starting a company in a different technology. And I was, I'll just say, gracious with them. It took me a few meetings to tell them that I thought that this was a very bad business model that I wasn't interested in working on. And then, Daniela, with her, I would say, delightful way, suggested that I come and see her autonomy technology on a Friday afternoon. And I said, no, I don't want to come. And she said, no, but you have to come. And I said, no, I don't want to go. No, you have to come. And so I got to MIT, to the Stata Center one Friday afternoon, and there were a couple graduate students waiting for me. And I got into the little vehicle that they were using and rode around, followed by a trail of graduate student ducklings. And the little vehicle, the little wheelchair performed perfectly, but the most interesting thing was that at the very end, we passed a woman who was a graduate student who was in a real wheelchair. And so we met her. She stopped, she flagged us down. I stopped, I got out, and she drove around, a couple of tens of feet. And and it was just really a moment because she basically said, when can I get one? When's it going to be ready? This would change my life. I'll have full, no pun intended, autonomy of my life. And, I talked to Daniela and we sort of said our kids, all parents who work are driving around their kids with white knuckles in Boston in traffic. And we would be able to trust our kids and to get rides and we would save time and life would be better. And so that was we really started this company to make the world better. That's for sure. And I led Venti into moving over into moving goods because it's a much simpler technological solution than doing something in downtown where all the people and the level of mathematical level of chaos is so much higher. And I'm really pleased because the supply chain needs our help. I mean, look what happened last time. If we had, I'll just say one last thing. I was talking to the head of the Singapore port recently in a meeting, and what we realized in the meeting at the very end was that there's actually the technology that we're going to have a fully dark port in 15 or 20 years. Fully dark, right? Autonomous cranes, autonomous trucks. It'll be like a factory now, a dark factory. That's where we're headed with this technology. And it's going to save so much money in transportation costs. We're already up productivity by 25%. So, that's kind of the story, and it's pretty exciting for the world.
thank you. Yeah, I'm really grateful you and Daniela doing this because from one side, US has the best robotics, best automation, best authorization, but our ports, Long Beach, they rank literally the bottom in the global productivity rank there, right? So glad you guys are pushing the frontier, actually get it down there. Daniela, back to you.
So we're going to push the frontier with very energy efficient solutions, which we are developing at MIT. Now, speaking of energy efficient solutions, I'm sure you have all read about DeepSeek, which introduced very energy efficient solutions and kind of paralyzed the conversation around AI. And so I kind of want to explain to you exactly what they did so that it's really clear that the advance is really primarily an engineering advance and not a conceptual advance. So frontier AI systems are built in two phases. There's a pre-training phase and there's a fine-tuning phase. And in the pre-training phase, what you do is you take a lot of knowledge facts, usually on the order of 1 to 15 terabytes of data, and you use this data, you feed this data as input to a model, a machine learning model, which is typically transformer based, which means it's feed forward, which means the model always looks forward, never looks back. And so you do that so that the model figures out the parameters, and the parameters are then used to do next word predictions. For instance, if you feed the sentence, the first ISSCC was held in, the number is 1954. Or if you feed MIT is located in the city of, the model will say Cambridge. And so this is hugely energy expensive, because you take all this data and you have to pass it over and over and over and over again until the parameters stabilize. Now, the fine-tuning phase takes a pre-trained model and adds some specialized information to it. And so, for instance, you can feed to this model all the proceedings of a particular conference. And then you do this so that the model can then do specialized tasks. For instance, the model can follow instructions like summarization. So you can say, summarize the following paper for me, or summarize the talk that Heidi just gave. And so these are the two phases. And so these two phases actually are both extremely energy consuming. DeepSeek did not make any changes to the pre-training phase. They were very focused on the fine-tuning phase. And what they did was they engineered extremely well some state-of-the-art solutions. And the state-of-the-art solutions for obtaining simpler, less energy-intensive models typically fall in two categories. You can do pruning. Pruning means you're going to look at the model and eliminate the neurons and the parameters, the edges, the connections between neurons that are not so important. And so you make the model smaller in this way. Quantization means you're going to use less precision for the calculations of the model. So for instance, instead of using 32-bit floating point models, you end up using 8-bit integers. The computations are less precise, but nevertheless, they still carry on. And so DeepSeek essentially showed that you can get to the best performing model much faster and using much less energy than it was previously thought. And they did this by integrating pruning, by integrating quantization, and by using other engineering tricks. Another important thing they did was that they coded their solution using PTX, which is the assembly language that sits right above the NVIDIA GPU. And doing all this, they have arrived at a structure that is much less costly than traditional solutions. So their current configuration for training costs $5.6 million for a single run. This was, but keep in mind, this was after they tried a lot of different combinations. So they spent a lot of money to arrive at a particular structure for their pipeline that ends up costing $5.6 million. And typically, this cost would be $70 million for a Llama 405B parameter model. So the DeepSeek models are 671 billion parameters. They're very large models. And then using these tricks, they're able to get the models down to a much smaller cost. So maybe that's all I want to say about DeepSeek. So what you should know is that there is really great performance, but there's not really innovation in the way the pipeline was set up. But there is really fantastic engineering, which is very important.
Thank you, Daniela. Buwa.
Yeah. Thank you, Gina. Thank you, Daniela, for that talk. As somebody who has the offline version of DeepSeek R1 on their laptop, it just amazes me that 20 gigabytes of this distilled version I can carry it around in my machine and use it whenever I'd like to without even the internet. So it's just fascinating. So we have a lot of questions, so I'll just jump, right into it. I mean, there are obviously people asking a lot of details, but please feel free to share what you can share. So the first one would be, what level from Salt Tannenbaum is what level of effort would be required to operationalize this technology for the next port after Singapore, mapping the rules, defining the environment that you spoke about, Heidi. And, is it required to build a whole new feature map for places where the robots would be operating, and what would be the cost, and how long would it take to recover the investment compared to human trucks? So the business case for it for a new port.
Well, that's an important practical, obviously, important question for the business. You recall that what I said today earlier is that the software system that we use has 3 layers. So the bottom one is the autonomy layer. It's where we started. And then as we developed the application for the ports, which I cannot overstate how deep that application is. It is rigorous, but it's also incredibly nuanced. So as I mentioned, we actually take the scattering of light that comes from a deep puddle and get rid of it. We actually can operate in heavy rain by mathematically taking out the raindrops. So the algorithms that we developed that are specific for ports are quite robust and deep. And what we find is that it's at least 85% of the software is used if we translate from one application area to another. So the movement between one port to another is significantly smaller than that. We expect it to be somewhere about 5% of the initial effort. Now, the initial effort was very high, of course, but the estimate's roughly 5%. And the other thing that creates that is that the robot has to make a feature space map of each place it's going to operate. And so by definition, we must start so far in an individual area, a specific area, and map it. That's actually quite fast because the way Daniela architected the system is that you just drive the vehicle around and the vehicle actually makes its maps. And we do it a couple of times and then we annotate those maps. And the annotation is actually, we do it from young, smart engineering students, frankly. We hire them right out of NUS and NTU, the universities there, and they can do this work really well. So it is knowledge-based work, but they're quite smart about it. And so the actual mapping for an individual place doesn't take us very long, but it is linear with the size of the place. But the last thing I'll say is that you saw that I told you we had scale mapping tools. What we've learned how to do is we built some tools where if, for example, a port has berths, for example, which are all the same, or a layout, which is replicated across the port, we can actually take that, overlay it into the new area from the old area we did, and then annotate the differences. So I can't give you specific numbers because ports are of all size, right? So it depends. We're working in a really huge one. It took us years for the first time. But I remember that when we first came out with this mapping tool, we had been mapping 40, I think it was 4 berths, four areas. And we had to do like 18. And it took us like a year and a half to do 4. Then we came out with a mapping tool and it did the rest in 2 weeks. So boom. So that's an answer to the question.
Thanks for that. There was a couple of questions on the technology, as in, is there any dependence on real-time connection with cellular networks, towers, or satellites for the functionalities of these AVs? Or do they have like pre-programmed waypoints and everything is closed and on-site for the positioning?
The core autonomy is all closed. And then we have to speak, for example, we have to connect to the remote operators. So we do have to do that. And we have special networks that we use that are proprietary and owned by our partners to do that sort of thing.
So it's a closed network, but the core autonomy is a fully closed system. So there's no communication to a cell tower or a satellite. All right. Moving on from the technology aspect to a more societal and political question, there were a couple of points on, what are the potential impacts of employment? And I know this is more about the PSA and the unions at the PSA for the employees. Are people being retrained for other jobs? I know there are currently only 30 vehicles, but will there be opposition from drivers who possibly may be part of unions? And just curious about your thoughts, because there are 4 or 5 questions on the same theme.
That's interesting. Well, it's interesting to me to find out why there were 4 or 5 questions on that theme. That would be something I would ask the audience. But basically, what our customers tell us is interesting is that actually it's not an issue for them. And the reason is, first of all, we do take the drivers and we retrain them to be remote operators. And they love that because they end up with a new age job, right? They're not driving anymore. They're doing something really
Is that 1:1?
back to their kids. No, it's not 1-to-1, but we get a number of those. But the more important issue really is that when you deal with a facility, you don't end up making an investment and rebuilding your whole fleet in 1 year. Those guys have, 1,000 vehicles, 500 vehicles, 200. There's no way you do that. So you do it over time, so they don't expect there to be a problem.
Well, I might also add that every new technology might impact how some jobs are done, but creates new jobs. And this has been happening since the beginning of the Industrial Revolution. In fact, David Otter has a slide that shows how more than 60% of what we do today did not exist before 1948. And so the world is moving and technology is changing the jobs. We think that the jobs that are being created as a result of this technology are doable by anybody and everyone, and they are more exciting and interesting to the people who work in these industries. And so then the other thing is that there aren't enough people in order to do all the jobs that need to be done. So it's useful to think about collaborative human machine teams where the machine is viewed as a tool, as an intelligent tool that supports people and enables people to do more.
True. I think we're hearing similar threads from the autonomous trucking industry, where there's a truck driver shortage, and we can use our AV trucks to, reduce the impact of that. One question was, can you compare or contrast your system to the older Frog automation system for ports originating from the Netherlands? Not sure if you've heard of that. And also there's another MIT startup, IC.ai, doing autonomous yard trucking. So I'm sure, just any thoughts on, their systems as well?
Well, I haven't heard of the first one. I saw Daniela. Do you know about that?
Well, I think that maybe what you the Frog automation system, I think, is the system where you put kind of breadcrumbs that allow the robots to follow. So it's not so the vehicles are not fully autonomous. They follow paths that are embedded that can be read in the roadways. I didn't think it was called, I didn't know the name. So I think this is what the Frog refers to. But it's essentially not full autonomy. It essentially leverages sensor networks and communication devices embedded in the road to help guide the vehicles. But the vehicles do not have the same independent capability of reasoning about the world and deciding what to do.
And any thoughts on IC.ai, another MIT startup in the autonomous yard trucking space?
I mean, honestly, I think IC's fantastic, and I wish them enormous success. There are a lot of similarities to the applications, but what we do has a lot more, I think, pieces to it. It's much more complex. But more power to them. I wish them great success, and we'll be right there alongside with them.
Yeah, I think I'll get one last question in. There were a couple of questions on the disaster resiliency, and if there is a major disaster or emergency, how long before you can get your system to a full stop? And do you experience or have you experienced disengagements or any sort of accidents that you can publicly share in the forum?
Oh, that's a really interesting question. And I'll tell you why. When we were building the system to go from a development system to actually operational, it was so hard. I can't remember who said something about Daniela, it was who said that. It was so hard. And, as the CEO of the company, I kept telling them, I don't want my face on the cover of Time magazine. We have to be careful. Safety first, safety first, safety first. So we ended up developing a philosophy for the vehicle that basically any whiff of an issue for the vehicle in its logic and its programming, it stops. It stops, right? Just make it stop. And so we went through this phenomenally difficult and rigorous process where we looked at every single component, hardware and software, in that damn thing to make sure that we would have what we called a safe stop as a default. And because these things can weigh, as I said, 8,000 pounds, right? So the last thing you want is, as I used to say, an 8,000-pound robot running amok, right? So we did this excruciating work under, by the way, the leadership of James Fu, who you guys may have heard of, but he was the first person who left the MIT academic area. He's a postdoc of Daniela's, to found autonomy way back when. So he actually led this because he was personally so committed to the whole safety issue and because he felt like it was his name on this risk, right? So in the end, we ended up having, in all of our operating time, just one incident that could have been scary. And you can, as you understand from what I just said, that could have been scary. We had incidents, but basically this whole safe stop thing worked. And so that's kind of what I would tell you, is that it's obviously a work in progress. We've been doing this for years. As I showed you, whatever it was, a couple of 100,000 kilometers of time run. And, we look every day for these incidents. But that's the best I can tell you, is that our lived experience so far has been fine. Now, I'm not arrogant, and there's a long tail on the whole software build. And you just live in the real world with this risk of this tail. And back to what I said at the beginning, I like this application area because an enclosed environment with almost no people around and no drivers is a very much safer, from a catastrophic risk perspective, environment than the robotaxi application. So I'm not hubristic. We are really careful, and every time we have anything that's a little odd, we investigate it immediately. We can shut the whole system down. We actually have rarely done that because our partner is confident with us. But we just take every day seriously, knowing that something could come bite us. So I don't know if that's the answer, but that's our lived experience.
No, that's a great answer. Thank you. Over to you,
Yeah,
Siddharth.
great. Yeah, so sorry to interrupt the warm conversation here. We're running against time. Also, we didn't get time to really discuss what Daniela presented. both on the introducing the barrier net, additional layer to really offer the safety guarantee. This is such a critical, point. Thank you, Daniel, for introducing it. Also, the previous one, combining vision and language model to have this auto-distribution generalization, such a powerful research there. Heidi and Daniela, thank you so much. I will invite you again to give a more substantive presentation. Everyone, please join me. Thank Daniela and Heidi.